Hello everyone and welcome to the course of Nanobiophotonics touching our daily life. So we are in the week 3 of the problem solving discussion. So I am Udiptya from IIT Madras and today we will be discussing on this 5 topics: facts of matter, introduction to nanotechnology, the art of small, synthesis of nanomaterials, top-down approach and applications. So what we understood in the first facts of matter, if I want to recall, is one of the important thing is uh, we understood that both light and matter exhibits dual nature. Yeah, we have both wave and particle. Yeah, wave and particle nature, and then we also understood about polarization of light, which refers to the orientation of the electric field with respect to its propagation. Yeah, then we understood the quantum conditions for the energy states of matter, which are derived from the solution of Schrodinger equation. And from that we understood that energy levels of electrons in an atom is quantized, and these atoms try to lower their overall energies. And they try to be in the stable form by lowering their energies. And then understood the concepts of bonding, in which constructive overlap of atomic orbitals produces bonding, and destructive overlap produces anti-bonding. Yeah. So this intermolecular effects also we understood. Yeah. Then coming to introduction to nanotechnology, so you understood what nanotechnology is. Yeah. So in nanomaterials we have to have uh, we have to have like one of the dimension in the range of 1 to 100. Yeah, that's basically what we understand in the nanotechnology. So we understood what are the different types of nanomaterials, and then the properties of nanomaterials. Yeah. So yeah, then so its classification. Yeah, because of zero dimension, it is basically um, all the dimensions are in nano scale. Then you have one dimension, two dimension, and three dimension, based on the dimensions. Yeah. Then they have unique set of properties like electrical, mechanical, optical, physical, can be magnetic, several properties. Yeah. So these unique properties usually are attributed to the increased surface area to volume ratio and the uh, quantum confinement. Yeah, high surface to volume. This ratio is high. Okay, and quantum confinement. These are the primary causes. Yeah. So in the next one, nanotechnology, the art of small, we learned. Um, so it was kind of we learned about the different nanomaterial synthesis techniques. Yeah, lithography and most of the bottom-up approach we learned here. So then we learned on the top-down approach, in which it was like the methods here are less complex and also economical compared to the bottom-up approaches. So lot of methods you learned on ball milling, liquid phase, exfoliation, and laser ablation. Yeah, ball milling, in which we involve crushing of bulk precursors in using some balls, yeah, which are usually made of tungsten carbide or stainless steels in a vessel, and rotate them such that rotate them in a high speeds. Yeah. Then you have liquid phase exfoliation, in which uh, bulk materials broken down into by using ultrasonic waves. Yeah. Then another one is laser ablation. Laser ablation. So laser ablation means vaporizing material substance in a liquid medium and the further nucleation and condensation of the vapors, leading to formation of nanoparticles. Then on the application side, we usually saw material specific applications here. We saw how quantum dots can be helpful due to their photoluminescence effect. Yeah. Then we also go on saw some two-dimensional nanomaterials like graphene. So yeah, so that was the quantum dot and other effects. So let's go to the questions. So which of the following is an example of a bottom-up approach in nanotechnology? So the answer is self-assembly of nanoparticles. Okay. So here you can see. So self-assembly of nanoparticles is a bottom-up method where nanoparticles spontaneously organize into ordered structures driven by their inherent properties and interactions. This process mimics natural systems, allowing precise control over nanoscale arrangement without external manipulation. While leveraging factors like particle size, shape, and intermolecular forces, intricate patterns with tailored functionalities can be achieved, finding applications in diverse fields such as uh, electronics, and medicine. Okay. So the answer will be self-assembly of nanoparticles. Which property of nanoparticles make them suitable for targeted drug delivery? So the answer here is high surface area. Yeah. So what happens in during targeted delivery? So what we need is because the nanoparticles are here. Yeah. So nanoparticles has to have high surface area so that you can load more drugs, yeah, on it. So this will enable high efficient drug loading and interactions with targeting molecules and enhanced cellular uptake also. So this results in improved drug bioavailability and controlled release and prolonged circulation. Their multifunctional nature allows for attachment of various components such as imaging agents. So what you can do is you can attach imaging agents here, some targeting like some receptors like specific receptors like antibodies or DNA, which can bind to some specific receptors or cells, or you can bind some dyes here. So whatever you can functionalize easily nanoparticles, and then you can put the uh, uh, receptors contrast agents. So size dependent effects further enhance tissue penetration and cellular internalization. Overall, nanoparticles high surface area maximizes therapeutic payload, selective targeting, and therapeutic efficacy while minimizing off-target effects. So this holds great promise for advanced and personalized medical treatments. So what is the significance of scanning tunneling microscope in nanotechnology?
So the answer is STM is used for imaging and manipulating individual atoms and molecules. So STM, what how it works is it has a sharp tip, and that tip can actually move over the sample surface. And what it does it measures the tunneling current. So the precision, yeah, that the resolution that it works on is basically it can visualize individual atoms such that it can unveil sub-nanometer topography, and it precisely manipulates molecules by voltage pulses. So this informs nanoscale surface properties, aids material design, and fuels nanotechnological advancements, including molecular transistors. STM's unique capabilities provide insights and tools for exploring and engineering the nanoscale world, driving scientific understanding and technological innovation. Which method is commonly used for the synthesis of nanoparticles with controlled size and shape? So the answer here is a bottom-up approach in which it is favored by synthesizing nanoparticles with controlled size and shape due to its precise manipulation of molecular interactions. So by leveraging inherent properties, this method allows thermodynamic control, yielding uniform structures. So this atomistic manipulation enables tailored properties and intricate architectures, which are usually difficult to achieve through top-down methods. Bottom-up techniques ensure consistency, scalability, and versatility, making them suitable for industrial applications also. And they offer tailored surface chemistry crucial for functions like drug delivery, diagnostics. Overall, the bottom-up approach empowers the creation of nanoparticles with desired characteristics, advancing nanotechnology by harnessing self-assembly principles at the molecular level control. Okay. Which technique utilizes the high temperature decomposition of precursor compounds to form nanoparticles? So the answer is CVD, which involves high temperature decomposition of precursor compounds in a controlled environment to generate nanoparticles. In this process, gaseous precursors react on a heated substrate, leading to the deposition of solid nanoparticles. So the high temperature facilitates chemical reactions and enables atomic level control of growth mechanisms. CVD allows for tailoring nanoparticles by adjusting precursor composition, temperature and pressure, and that's why it finds applications in various fields from thin film coatings to nanomaterial synthesis. What is the key characteristic of 2D materials that distinguishes them from bulk materials?
So 2D materials possess distinctive electronic and optical characteristics that set them apart from bulk materials. Uh, Quantum confinement leads to modified band structures, resulting in altered electronic behaviors like tunable energy gaps and enhanced or suppressed electronic states. Their atomically thin composition induces strong surface interactions in influencing electronic structure and reactivity. So the answer is unique electronic and optical properties. What is the primary application of thin films in electronics? So the answer is production of flexible displays. So the primary application of thin films is electronics is production of flexible displays. The thin films play a crucial role in creating essential components of flexible displays such as organic light emitting diodes and thin film transistors, TFTs. Yeah. So you know about OLEDs, yeah? OLEDs are thin organic layers to emit light, while TFTs often based on amorphous silicon or other semiconductor materials. So this thin film based components, they enable the creation of lightweight, bendable and energy efficient displays that we can integrate into various devices like smartphones, tablets, wearable gadgets, curved or rollable screens. Yeah, now we have seen the fold mobiles here. So they have this kind of thin film based displays. Yeah. So this technology revolutionizes the design and functionality of electronic displays, allowing for innovative and adaptable user experience. Yeah. What is epitaxy?
So it is a process of creating thin films with high degree of atomic order. So FATX is a precise process used to create thin films characterized by a high degree of atomic ordering. It involves growing a crystalline layer on a substrate, but the arrangement of atoms in the deposited layer follows the crystal structure of the substrate. Okay? So you can understand the crystallinity, yeah, because crystals are ordered structures. So there's these are formed on already, like it follows the crystal structure of the substrate itself. Yeah, so that's why you get very well aligned and continuous lattice. So it will have very minimal defects also, and that's what promotes its uniformity. So they are used in semiconductor manufacturing, enabling creation of high performance devices with controlled electrical and optical properties. The process finds applications in ICs, optoelectronics, and other advanced technologies where material quality and precise atomic arrangements are critical for optimal device functionality. So where the quality and precise arrangement ordering of atoms are important, there you will find the application of epitaxy. So this is a numerical. So you have to tell how many gold atoms lined up in a row would fit in 1 nanometer space. So these are options. Sorry, yeah, I didn't add the. So the covalent radius is given. So the covalent radius is given 0.144 nanometer. Yeah. So the number of atoms which can fit in one, so we can write. So covalent radius is basically if we have two nanoparticles like this. So this is the covalent distance and this is basically covalent radius. Okay. So number of atoms will be equal to 1 nanometer divided by 2 into the covalent radius. Yeah. So which comes down to 1 by 0.288, which is 3.47. So the answer will be 3.5. So this is a assertion reason question in which the first assertion is the AFM measures the force of attraction between a probe and a sample surface. The reason R works only on the conductive samples. So the answer is only assertion is correct, yeah, because AFM does not work on only on conducting samples, unlike STM. So, uh, but it works on the forces of attraction. Okay? So only the assertion will be correct. So depending on the force, like this will be, if this is the tip, yeah, and you have material like this, so there will be interaction here, yeah, and that's what this probe, AFM probe will vibrate accordingly, and that usually how the AFM works, but it does not need to be conductive. So main thing. So only assertion is correct here. A material with one dimension nano range and the other two dimensions are large is called a So the answer here will be quantum well, yeah. The material with one dimension nano range and other two dimensions are called quantum well. So quantum well will have two dimensions in nano range, yeah. Only one dimension. Quantum dot will have all the dimensions in nano range. So if a spherical material with a radius of 10 micron disintegrates into a group of particles with a radius of 10 nanometer, her total volume remains constant. The increase in surface area is by a factor of. So we will solve it. So we have to first say what is given here. So it is given that initial radius r1 is 10 micron and r2 is 10 nanometer. You know, V constant. So we know that volume, yeah, is volume of a sphere is 4 by 3 pi r cube. Okay. So so what we know is we can find out the number of small particles here, n equal to, so n into v2 equal to, it will be v1, yeah, because it will be disintegrated from the v1. So from there n equal to v1 by v2, yeah. So when we do that, 4 by g by r1 cube 3 by r2 cube so r1 cube divided by r2 cube, yeah. So the total surface area, yeah, total surface area will be n into 4 by 4 pi r square, yeah. So it will come as, so n you can put that as r1 cube by r2 cube into 4 pi r2 square, yeah. So now we have to find the factor of increase. So the factor of increase is equal to a2 by a1, yeah. So a2 is 4 pi r, sorry, r1 cube by r2, yeah, that's what we get from this, and divided by 4 pi r1 square. So we get r1 by r2. So we substitute our values.
So 1 micron is essentially 10,000 nanometer. Divided by 10 nanometer. So which comes to 1000.
Yeah. So it increases by a factor of 1000. Okay. So if any doubts you have, you can ask, or otherwise we'll close the session.